Andrew Cleland is the John A. McLean Senior Professor of Molecular Engineering at the University of Chicago and Senior Scientist at Argonne National Laboratory, Fellow of the American Physical Society and the American Association for the Advancement of Science. He's going to tell us about hybrid quantum systems, outsourcing, superconducting qubits.
Thank you, Professor Halperin. I would also like to thank the American Physical Society as well as the Kavli Foundation for inviting me here and giving me an opportunity to talk about this work. Now, originally I was going to talk more about the hybrid quantum systems part and less about superconducting qubits, but I think in the interest of making an interesting talk, I will focus more actually on the superconducting qubits part and lean heavily on work that I did in collaboration with the group of John Martinez with theory input from Mike Geller, Sasha Korotkov, and Frank Wilhelm. Now, superconducting qubits date back, I think it's fair to say, to the dates of work on macroscopic quantum tunneling in the mid-1980s. But the first superconducting qubit that showed coherent oscillations between the quantum states and quantum control of these qubit states was really done by Yasu Nakamura then at NEC in this seminal paper published in 1999. That was followed by work from the Saclay group where they showed that they could make a device called a quantronium in 2002. John Martinez at NIST then in 2002 with the phase qubit, and finally in this series the flux qubit from Hans Muey's group at Delft in 2003. Now these four different types of qubits, superconducting qubits, of which there are actually a variety more of these, all rely centrally on the Josephson effect in order to provide the qubit functionality. And I will try to describe how that works in a very simple example. However, I do want to next introduce what I think was really kind of a game changer in this area, which was the invention and demonstration of the transmon qubit by Rob Shilkoff's group at Yale. This very simple device, which is just a junction in parallel with the capacitor embedded in a transmission line resonator, really kind of made things a lot easier for everybody. It's a device that is very easy to fabricate. It has a very simple scheme for reading out the qubit states. And very importantly, it has consistently long coherence times, both in the energy lifetime and perhaps more importantly, in the phase lifetime. And this was demonstrated by an early paper. This was a 2008 paper showing few microsecond T1 relaxation times in these devices. And they work in the same sort of parameter range as the other qubits with gigahertz frequency transitions for the ground to excited state splitting, and harmonicity, which is very important, and I'll talk a little bit more about, of a few percent between the first two levels and the third level. Strong coupling possible to the readout resonator, and very importantly, good T1s and T2s, for instance, typically in the sort of 10 microsecond regime, as was shown by this paper from Rob's group in 2012. Now, the way the transmon qubit and some of these other qubits work is really based on a very simple electrical circuit, the LC oscillator, where if one looks at the energy, for example, as a function of the magnetic flux linking the inductor, one finds this parabolic shape, and that is the potential energy of the oscillator. The kinetic energy is the charge on the capacitor, and one then has a harmonic oscillator with a resonance frequency given by the usual 1 over square root of the inductance times the capacitance. You can easily make circuits like these that work in the gigahertz range, and if one looks at the quantized energy level structure one expects for a harmonic oscillator, if one wants to cool a few gigahertz frequency oscillator to the quantum ground state, one needs the operating temperature, kT, to be much less than the spacing of these energy levels. So when you're working in the microwave range, this means you need to work at temperatures less than about 1/10 of a Kelvin. That is, however, not such a challenge these days, and combined with the straightforward packaging, cabling, and control and measurement electronics that are available to us from the telecom industry, developing cell phones in the same frequency range, these are really fairly simple circuits to design and manipulate. However, these are not qubits because you have the harmonic energy distribution prevents you from addressing any single pair of the energy levels in this circuit. So you need some type of energy level and harmonicity to enable quantum control. And this is, of course, provided by the Josephson junction, which is the key device that's provided to us by superconductivity. These junctions are fairly simple to make. Here's an example of an aluminum oxide aluminum junction where you have a thin insulating barrier separating these two completely conventional superconductors. If one writes down the Josephson relations for the current and voltage of this junction, they have this form right here, where phi is the phase difference between the superconductors on opposite sides of the junction. And one can combine these two equations to make this junction look like a nonlinear inductor, showing that the voltage is related to the rate of change of current with time through this effective inductance that depends on the phase. And this is the nonlinearity that is so key to making these devices work in the quantum limit. You can write down the circuit Hamiltonian, impose that the, so that you get the, this cosinusoidal energy as a function of the phase, quantize this by enforcing that the phase and the charge be conjugate variables, similar to position and momentum for a mechanical system, and then solve for the quantum energy levels in this system. And given this cosinusoidal dependence, the spacing between the ground and first excited state differs from the excited to third level, which I've labeled F here, by a few percent. So basically, the way you think about this circuit is that the Josephson junction is effectively an inductance, but the value of the inductance changes with each excitation, each photon that you store in this circuit. So the qubit levels, when you want to use this for quantum information purposes, are the lowest and first excited state. These are easily designed to be in the few gigahertz range, which is convenient from the technological point of view. And the anharmonicity separating these from the third level is, as I said, a few percent. Now, if you slightly modify the circuit by adding another junction in parallel, you get a squid, much like the ones that Dale talked about in the previous talk. And by linking some magnetic flux to this effective squid loop, you can tune the frequencies, the splitting between the ground and excited state, as well as between the excited state and the third level. Now, very importantly, the limitations to the performance of these devices are really determined by materials. So, for example, the qubit T1 lifetime in most devices is probably limited by loss in the capacitor, rather than anything to do with the junction. And the phase lifetime, so the lifetime for separating states on the equator of the Bloch sphere, is limited primarily by flux noise, which is a topic that has plagued squids for 30 years, and I think only in the very recent few years has begun to be improved, primarily by work from Robert McDermott's group at Wisconsin. Now, these qubits are fabricated using semiconductor processing technology. You can make them on large wafers all in parallel, and you do this in a clean room, of which there are probably 10 or so in the United States that can do this. This is a facility at the University of Chicago that we use in order to make these types of qubits. The style qubits, of course, depends on how you want to use the qubits, what sort of designs you want to use. This is an example of a variant of the transmon qubit that was developed at UCSB. It's called the Xmon qubit. The qubit itself is down in the bottom of this image. where I've zoomed in to the very bottom of this cross-shaped structure right here in the upper right, showing the Josephson junctions that are key to this device. There are two in parallel in a flux loop that allows you to tune the frequency of the qubit. So those junctions provide the inductive part of the circuit. The capacitive part is provided by the capacitance of this cross-shaped structure to the surrounding metal ground plane. And that's our LC oscillator. Now, in order to control the qubit, there are a pair of wires that are coupled to the qubit. Coming down from below here, shown in detail up in this upper right, is the Z control line. This couples flux into this flux lock loop and changes effectively the critical current of the parallel junctions and thus tunes the frequency of the qubit, which turns into an effective rotation about the Z-axis in the co-rotating frame. Another line comes in from the right here. This is the line that's used for XY rotations about the block sphere by applying microwaves in either quadrature at the qubit frequency to affect those kinds of rotations. Measurement is done using this dispersive readout scheme where you have a microwave resonator, that's what this structure is right here, that's coupled capacitively to the junction at one end and coupled inductively to a measurement transmission line up here. And the basic idea is that this readout resonator, its frequency is determined in part by the loading of the qubit. And because the qubit's impedance changes when you put a photon in the qubit, this slightly changes the resonance frequency of this readout resonator. And by probing that resonance frequency, you can projectively measure the state of the qubit. And then this fourth wire right here, this is a microwave resonator that was used to couple to other qubits. So these devices are fabricated on substrates of either typically sapphire or silicon, chosen for their very low dielectric loss. You pattern them into chips that are a few millimeters on a side. These include wire bond pads so that you can make electrical connections to the control wires. And then this type of chip is diced up and placed inside some sort of mount to which you make wire bond connections in order to actually talk to the qubit. This mount is then placed on the mixing chamber of a dilution refrigerator, which typically goes to a temperature of, say, around 10 millikelvin. You can design very complex circuits, but often you can't operate them properly. So that's always the biggest challenge. Here is an example of one of the more complicated circuits that we developed at UCSB. This is a 5-qubit linear array, so you have 5 qubits in a row. Each qubit has a pair of control lines, one for Z control, the other for XY control, and then the qubits are coupled to one another via capacitive coupling. Each qubit also has a readout resonator that are coupled to a common measurement transmission line. And the coupling between the qubits is achieved simply by capacitive coupling. So this device was used, for example, to benchmark the operation of the gates that are needed in order to basically build a quantum computer. So these gates were applied to each of the qubits after it had been tuned up. But after tuning, no further adjustments were required in order to get these kinds of numbers. So this is testing each one of these gates using a technique known as randomized benchmarking, which basically means that you repeat the gate as many times as you can in order for the gate errors to dominate over state preparation and measurement errors. And from those measurements, you can extract what the fidelity of the gate itself is, even in the presence of fairly strong state preparation and measurement error. So what you see is that for these qubits, you can get fidelities in excess of 3 nines with an average of about 3.5 nines fidelity. In addition, we were able to implement a controlled Z gate. This is an analog to the controlled NOT and can be turned into a controlled NOT by adding single qubit Hadamard gates. And this controlled Z gate was done in a 40 nanosecond execution time with a fidelity of 2.5 nines. And to compare, the state preparation and measurement fidelities are significantly worse than these numbers, typically around 90%. Now, this 5-qubit circuit was used to execute this piece of quantum code, showing the 5 qubits being sent through a series of single qubit as well as controlled Z gates. And this circuit was basically designed in order to generate sequentially a 2-qubit Bell state, a 3-qubit GHZ, all the way to a 5-qubit GHZ state. And the fidelity of the states then measured. And this is a fairly typical result showing 80% fidelity for the 5-qubit GHZ state. This fidelity is completely dominated by state preparation and measurement errors, not by the errors in these individual gates. Now, this work was then extended to this 9-qubit linear array. This picture is very famous. This shows the sequence, again, a linear array of 9 qubits. The idea here is that this was basically a section taken out of error protection architecture called the surface code that I'll talk about in the next slide. And basically, the idea is that of these 9 qubits, you have 5 data qubits colored in blue, interspersed with 4 measurement qubits colored in green. And the idea is that the measurement qubits measure the product of the Z operators on the adjacent qubits. And by measuring these, you can detect X bit flip errors in the data qubits. And this circuit basically works, but in order to really go past this and build fault-tolerant architectures, you need to scale up to 2-dimensional arrays. There's a great deal of activity going on in this direction. John Martinez and his group have moved to Google. They are now scaling up these types of devices to much larger arrays, as is the team at IBM and the team at Lincoln Labs, as well as a few others. Now, I think the goal of a lot of this work is to try to demonstrate a fault-tolerant architecture, an architecture that can detect errors in the physical qubits and yet have logical qubits with much better performance. Now, the simplest architecture for doing this, when you have a planar array of qubits, is the surface code. This is the structure of the surface code. It's a square array of physical qubits. Those are shown by the open circles and the closed circles in this grid. The open circles, which make up half of the qubits in this image, are the data qubits. That's where you store the computational state of the system. And the black solid qubits are ancilla qubits that are used to measure and stabilize the adjacent data qubits. The ones in green do a measurement of the 4-fold Z operator of the adjacent data qubits, while the ones measured in yellow measure the 4-fold X product of the data qubits. And these are done by having the measure X and measure Z qubits, ancilla qubits, perform a sequence of operations on the 4 adjacent data qubits. And every cycle of this every cycle of this of the stabilizer operation terminates in a measurement of the qubit that will signal if an error has occurred either in this quantum circuit or in the data qubits or in the measure qubits. Now, if you have sufficiently high fidelity in both the idols as well as all of these gates, then you can actually use this type of architecture to get much better improvement in arrays of qubits than in the individual physical qubits. In order to achieve that, you need an overall fidelity of better than about 99.5%. And that's just where the transmon qubits are today. So they're right at the verge of being able to achieve this kind of fault-tolerant architecture. Now, we can look very briefly at how the surface code sort of acts in order to give much better logical performance compared to physical performance. If we assume that we have an error rate that's 1/10 of the threshold, so this is about an order of magnitude better than what has been demonstrated so far, then you can make some rough estimates for how big a surface code array you need in order to get improvement. And this depends on what your tolerance to error is. So for instance, if you just want to build a single logical memory qubit from an array of physical qubits with this kind of operation, and you want your logical qubit to have roughly a factor of 1,000 smaller error rate than the underlying physical qubits, you can do this with an array of about 600 physical qubits. If you want to get 1,000,000 times better performance, you can do this with roughly 3 times that number of physical qubits. And if you want 1,000,000,000 times smaller rate, you can do this with another factor of maybe 2.5 more times physical qubits. So this kind of exponential scaling in the error rate with the size of the surface code is a signature of this kind of approach. If you want to build a circuit to demonstrate a topological controlled knot with 1,000 times smaller error rate, you need about 2,000 physical qubits. And then if you ask the hard question, what if you want to build a prime factoring Shor algorithm computer that you want to build to factor, let's say, a number with 5 decimal digits, you need about 40 million qubits, while if you want to factor a number with 600 decimal digits, you do need something like 1 billion qubits. So, sorry, 1 billion qubits. So these are clearly very, very challenging numbers. And there is still a lot of improvement that needs to be made with the qubits in order to even hope to achieve this. So significant improvements are needed in the T1 and the T2 of the physical qubits. The controlled knot error rate is still kind of high for going after this kind of goal. Stabilizer circuits have not yet been demonstrated. I think that's kind of next in the path. There's the question of what happens if you have long-range correlated errors in the surface code. I don't think this is known. And one can come up with many other questions to ask. So there are other more limited targets that one can look at. For example, quantum simulation is a popular one. You can build small quantum simulators with existing physical qubit systems. I think this is going to see a lot of growth over the next few years. Quantum-assisted annealing, this is, of course, an area led by D-Wave, trying to solve optimization problems by doing adiabatic computing, a very different approach from this kind of gate-based computing. And then Google has explained that they think that there might be applications in quantum sampling where you can sample probability distributions more effectively using a limited number of qubits than you can do with a classical computer. I think another area that's very interesting, which is the hybrid part of my talk, and this is just the last couple minutes, is can one use superconducting qubits to couple to other things? For instance, to spins, or to try to achieve long-distance qubit coupling, meaning over distances larger than the size of a cryostat. And what's very encouraging is that the transmon qubit has some very nice numbers in terms of its fundamental parameters. If you just look at the effective junction inductance and capacitance, you can work out that the characteristic impedance for a qubit is around 300 ohms, very close to that of free space, which means that these types of devices should enable very easy engineering and coupling to other systems. So I think that superconducting qubits have a really interesting future as quantum enablers for other types of systems. We've done some work in this area. So for example, you can very trivially couple a superconducting qubit to a microwave resonator and develop methods for programming in synthetic quantum states and then reading them out using a technique that was developed at UCSB called Wigner tomography. You can couple superconducting qubits to mechanical devices. So this is an example of a microwave frequency mechanical resonator coupled, in this case, actually to a phase qubit, in which we were able to demonstrate cooling to the quantum ground state, as well as measurement of mechanical qubit Rabi oscillations, so that you could effectively program a single phonon into one of these resonators. We're now trying to extend this to work coupling a qubit to a surface acoustic wave resonator. If you want to hear where this work is at, you can hear this talk by Kevin Satzinger in session V13. We're looking at coupling superconducting qubits to spins. This is an effort in collaboration with the group of David Aushalom, looking in particular at the neutral divacancy in silicon carbide, This is a long-lived spin state that has optical readout and very conveniently is placed on inside a piezoelectric substrate. And so we'd like to look at coupling superconducting qubits to these spins via phonons, building structures such as this kind of Gaussian optic structure shown here. And then finally, what we're trying to do is to develop a means for coupling superconducting qubits to light in a telecom wavelength, where the idea is that superconducting qubits at distant nodes could possibly communicate to light if one can convert coherently quantum signals between microwave frequencies at which the qubits operate and optical frequencies that you could send through a fiber optic. We're doing this by trying to develop one-dimensional optomechanical systems that were developed by Oscar Painter's group at Caltech. These comprise a dielectric mechanically suspended beam with a pattern of holes in it that traps a convenient telecom wavelength optical mode co-located with a conveniently gigahertz frequency mechanical mode. And through this co-location, you get strong parametric interactions between these frequencies that allow you to frequency convert. And by building these from piezoelectric materials, we can couple electrical signals from the qubits into these systems, so that one can imagine taking a laser signal and encoding gigahertz frequency sidebands using one of these structures, where, for instance, a quantum state might be encoded as these two phases of the sidebands with respect to the laser. In a first-generation device, we showed that we could take classical microwave coherent signals and program in single phonon sidebands into the detected optical signal. This is all room temperature, completely classical. And in a second-generation device, we showed that we could not only do that, but we could also take a modulated optical signal and generate electrically detected microwave signals and control the phase of the detected electrical signal via the modulated optical signal. So that's all I'm going to say. I think I'm just out of time. I'd like to acknowledge my current group members and thank again the American Physical Society and the Kavli Foundation. Thank you.
Thank you very much. Thank you, Andrew Cleland. Yes, questions?
It's a really nice talk, Andrew. My question is about how you're going to improve the fidelity of your qubits. It's an obvious question, but I'm sure a lot of people are interested. How can you get another factor of 10 or 100?
Well, I think there has only been very limited work on the materials questions in these systems. I think that, for instance, just to take one example, the work that Rob McDermott did showing that he could reduce the flux noise in squids by an order of magnitude by selectively removing oxygen from the surface of similar types of structures holds great promise for qubits. And it's possible that the same kind of surface treatment might yield an order of magnitude improvement in the flux noise limitations on phase coherence time in qubits. The T1 time, I think, is a little bit trickier, but I don't think that we've really applied the full panoply of material science techniques to try to characterize, identify, and eliminate those kind of defects. But I would say that there's definitely hope if there's a sufficient effort.
So you talked about how the Xmon could be used in this two-dimensional surface code. And I wonder, you went through the scaling of when you had a certain fidelity on one individual, how many you would need to do a logical qubit. Do you need to address every single Xmon in that array to implement the surface code?
Well, so if all you want to do is build a static surface code, you technically only have to address half the qubits, so the measurement qubits, because the data qubits aren't doing anything. They're projected into a simultaneous eigenstate through these repetitive measurements from the ancillas. But you do have to have wires going to every single one of the ancilla measurement qubits, yes. So Is that a challenge? Absolutely. Whether there are architectures that will allow you to do this without running thousands of microwave cables from room temperature into a cryostat, I think there's ideas out there.
So let's thank Professor Cleland again.